people with a little bit of revision, rates of reaction. Okay, so again, a little bit of a link to GCSE with a couple of things added in. So we'll start with the basics, collision theory. Okay, we all know this. A chemical reaction occurs, the particles must collide. Okay, for a reaction to occur successfully, the collisions must be with an energy greater to or equal to the activation energy. For a reaction, the particles' orientation must be correct. Okay, so what we're thinking about here is that normally whatever's happening, these particles by here will be bumping into each other. Okay, so these particles by here are going to be bumping into each other, colliding. It's only when these collide with enough energy are the bonds here and here broken, and then the bonds, new bonds reformed in their products. So these are our reactants, these are our products. It's only when they collide with enough energy. So they'd be bumping into each other, colliding all the time, only when they collide with enough energy. Okay, that energy then can be measured from a energy profile. So it's that hump there, we call it the activation energy hump. Okay, and there's the energy released or taken in a reaction to assure that it carries on. That's just an exothermic energy profile. So speeding up rate, there's four kind of main ways, but the big three are the ones that I've put on here as well. Surface area is the other one, but not used as much at A level. Okay, so temperature, we all kind of know what happens with temperature. You increase the temperature, so you've got your particles moving around. Say you've got 4 particles in a volume, you heat it up, they've got more kinetic energy. So they've got more kinetic energy, they're more likely to bump into each other, which means that there's more chance of collisions, more chance of successful collisions. Okay, increases the rate of reaction. Okay, it's all to do with that thermal energy, the heat energy, the temperature increasing being converted to kinetic energy. Okay, they're moving faster, they're more likely to bump into each other. Okay, looking then at concentration. Concentration is quite simple, increasing the number of particles. So say this is the low concentration, I've got 1, 2. Obviously they're in an area and they're going to bump into each other, but it's going to take them maybe quite a while to bump into each other, collide with enough energy. Now, if I add in another 4 or 5 particles, they're going to bump into each other because they're in the same volume, same area. It's just that there's less space, less space for more particles, so they're more likely to collide. Them collisions are going to lead to successful collisions, which means that there'll be a quicker rate of reaction. Okay, pressure just mentions with gases, it's the same kind of thing. Gas pressure tends to be that you force it down into a smaller area, but it's the same kind of thing. The particles got less, are more likely to collide. Then catalyst. Okay, catalyst is a substance that increases the rate of reaction without being used up. It provides an alternative energy path. So you might see this done a couple of ways. You might see it drawn on just a normal energy profile. So if you draw it on an energy profile, the second line I just drew would be one with a catalyst because it's lowered the activation energy. Obviously you draw that much better in the exam. There's 2 types of catalysts that you need to know about. So we've got homogeneous. Okay, they are in the same phase as the reactants. Okay, they tend to get involved in the reaction. They're not really an inactive spectator. Okay, it's typically with liquids. Stuff like sulfuric acid helping to form esters. Okay, and then you've got heterogeneous. Okay, they're in a different phase from the reactants. What they tend to do is they tend to be transition metals. They get absorbed on the surface, and it tends to attract the reactant particles, so that they all are bound on the top of the catalyst, and then it kind of weakens the bonds between the molecules, and that's why the bonds can then break, so the reaction will happen quicker. So measuring rate, again, quite a nice, easy. So big ways to measure rate then. Gas collection, we could do that with the syringe or with the measuring cylinder. Syringe is more accurate, you're just measuring how much gas is produced from a reaction, then you can measure the rate if you want, time, however you want to do it. Change in mass again, when reactions sometimes happen, there might be a new product which is gas, which means the mass will get lower, or you're forming a solid or a precipitate, which means the mass will get higher. So again, just placing on a mass pan balance, we can measure the mass. Okay, colorimetry is looking at the color change. Obviously you can do it with your eyes, the colorimetry is far more accurate. Okay, it uses light source, so it can measure the light intensity. Obviously, as the light intensity changes, it goes from like clear to a certain color. It'll be able to measure it more accurately, so you can kind of see how quickly the reaction is progressing. Okay, the main specified product for you is the iodine clock, which is where we used different concentrations of a hydrogen peroxide, and we added that to iodine and a thiosulfate, and there was a colour change that occurred. Then obviously once we've done that, we can then plot our results on a graph, and sometimes we'll be asked to use a gradient, plot on a graph. Okay, so these are my results. Imagine they said to get it at 20 seconds, that was 20 seconds there. Draw the line up. Okay, obviously with my ruler then, I would create my tangent line. That's absolutely terrible, you get the gist. Then I go even times either side, draw a line up, and then obviously from my tangent a line across. Same for 30, a line up and a line across, and then we do our difference in y over our difference in x. So our numbers for x would be 30 and 10, or try and do 30, take away 10 so you don't end up with a negative number. Then I'd look for my value for 10, say it was 20, value for 30, so that was 40, take them away from each other, and that would give you a rate depending on what we were doing. So say we had time along the bottom in seconds, and we had concentration in moles per decimeter cubed. Okay, so then the units for that would be moles decimeter cubed over seconds, or you can bring the seconds up and put it as seconds to -1. Okay, just checking your units there. And we looked at activation energy, so just a definition of activation energy you need to know. Activation energy is the minimum amount of energy required for a reaction to take place. In accordance with collision theory, for a reaction to occur successfully, particles must collide with energy greater than or equal to activation energy. Okay, on energy profiles it's shown as EA, where the peak of the energy curve occurs. And the final thing that is quite different from what we did at GCSE is looking at our Boltzmann distribution. Okay, so this is just the average Boltzmann distribution. Okay, it shows the number of molecules and then the molecules and how much kinetic energy they have, so how much energy they have to collide or to move, so then they can collide. Okay, molecules with great energy, then activation energy will collide with enough energy resulting in a reaction. Remember, all these particles by here are still colliding. It's only the ones past here that collide and form a reaction, so we want to get all our particles over this side. Okay, that peak there represents the most probable energy. Okay, and then you can kind of work out the mean energy as well. So that's just a Boltzmann distribution curve, and a little bit of an explanation about Boltzmann and his distribution curves. Now, what they tend to ask you to do in the exam is to add on to your average Boltzmann curve where you'd put something if something had happened. Okay, so if I just draw a normal one and I label that there, activation energy. So I've increased the temperature. Okay, so that means more particles are going to have activation energy. My most probable energy is most probably no longer going to be by there. So I've got to do, add one on. So if I look now, I've still got the same number of particles, okay, but shifted slightly so that there's more particles here that have got activation energy. Okay, that's just a bit of a rough diagram. Okay, but that's what you'd expect. Next one then, increasing the concentration. Increasing the concentration is a little bit different. So if I just draw a normal one, because when you increase the concentration, you're actually increasing the number of particles, okay? So it's just, so it would actually be higher up and over because you are increasing the number of particles. So by increasing the number of particles, you're obviously increasing the number that will have activation energy, okay? Catalyst is most probably the easiest one to draw out, same kind of thing. So there's your activation energy. If you add catalyst, the activation energy just increases. So more particles because it lowers the activation energy. You will be asked to talk about what's going on with the particles. So with this one, you'd say more particles, there's more kinetic energy because the thermal energy turns into kinetic energy. Particles can collide more, that leads to more successful collisions. More particles have activation energy, quicker rate of reaction. Okay, so you will be asked to talk about these as well. So obviously I've whizzed through this, just gone through like a basic overview of everything you need to know. So if something you don't understand, just email me, come see me. Thank you.